Alex Nicolau. I'm a professor here in the CS department in the Donald Brand School of Information and Computer Science. And I'm working as part of this SurfIT group on this project on classification of programs and program optimization for performance, in terms where performance means completion time, execution time, and trade-offs of that versus power consumption. And we're working with an undergraduate student, Andrew Del Campo, who is here. Oh, straight in front of me. And we're also working with Rosario Camarota, who's a graduate student. And so when I was asked to give this talk, I was told that I'm supposed to give you not specifically a talk about this particular project necessarily, but a talk about what it means to do research in my particular area and how do you get from undergraduate days to being a researcher. And I suppose that might, if successful, this might incentivize some of you to go to grad school. So I'm not entirely sure how to do that. And so, so the best way I could think of is I'll give you a little bit of an overview, a very, very short overview, because at the end of the summer, well, presumably Andrew will want to give a talk, presumably on the great results that he's getting. And so I don't want to steal the thunder or to preempt much of that. So I'm just going to give you a little bit of an overview of what this project is, more in terms of why this kind of thing is interesting and important in the bigger picture, the broader scheme of things. And then I'm going to tell you a little bit about my other research interests, current research interests. And then I'm going to tell you a little bit about how I got here. From undergrad all the way to being a fairly senior professor at UCI. So, I don't know that will turn out to be of any interest to you. If you wind up being all asleep, then we'll quit when that happens. So if you all close your eyes, we'll be done. If not, then I'll keep droning on till we're gone for about 40, 45 minutes. So anyway, at least you can have a free lunch. So, all right. So, what is this about? What it's about is dealing with power, performance, inefficiencies, right? So computers are consuming power, and while they're relatively power efficient compared to, say, things like a car, they're not as power efficient as one might wish. And in fact, the power consumption of machines, of computers, is an increasing problem. Not so much when you think of a laptop, even though there's a problem too in terms of, you'd like the battery to last as long as possible. And in fact, those of you that have an iPad have probably noticed that there's a qualitative difference between a laptop and an iPad, in that the iPad you can pretty much use and forget about power. And every so often you need to charge it. But it pretty much lasts long enough so that power is not a primary concern in your mind at all times. Whereas with a laptop, if you use it, if it's unplugged, you pretty much are aware all the time about power, because within a few hours, it's gone. And so there's a problem even there. But the power problem really becomes a really serious problem in two ways. One is in terms of cooling, which you may have also noticed with laptops. If you keep them on your lap for any length of time and watch a movie or something, they tend to heat up pretty badly, and there's a fan that turns on, and it becomes annoying. But, you know, and some of them you can actually get scalded by literally, I mean, it burns your thighs if you hold it on your lap for any length of time while doing significant computing. So that's a manifestation of the, you know, power problem. I mean, you know, it's dissipating a lot of power. And this is becoming, you know, a very serious problem in that if you look at the projections of how power dissipation increases per area of chip, it's literally approaching quickly the heat, I mean, per square centimeter, or per square inch, or per square millimeter area, it's approaching the heat dissipation of a nuclear reactor. So that's mind-boggling, right? I mean, it's clearly not tenable in the long run, right? I mean, if you see that curve, it's curving up sharply, and it's, you know, it's quickly approaching the core of a nuclear reactor, and it's not all that far off from, you know, I mean, I'm exaggerating, you know, on a logarithmic scale, but from the core of the sun. And so clearly we cannot go on with this. Obviously, you know, we won't get there because this cannot happen. But it's becoming a real major problem. What that means is that processors that we're building now are slower than we could technologically make them if it weren't for the fact that they would heat up to the point where they would burn out, literally, like burst out flames. And you know, of course, then stop working. And so this cannot go on, and it's a very serious problem. But even before that, even if we don't worry about this and we say, okay, well, we'll run at slower speeds, and that's fine. Power dissipation and power consumption is a huge problem in another way. Companies, big companies, like, you know, you've heard probably all about the cloud computing and all that. Well, cloud computing means somebody somewhere has huge numbers of processors that are available over the internet to serve you for whatever, for doing massive computations. But so Amazon, Google have massive farms of computers, thousands and upon thousands of computers in one huge room, which is air conditioned, but you know, because the heat dissipation again of all those processors, because of the power consumption, some of the power, because of the inefficiency of the computing, some of the power is dissipated as heat, right? Now the cost in just electricity is in the hundreds of millions of dollars aggregated over all those companies, rapidly reaching, you know, in the billions. Beyond that, cooling those rooms is a problem. It's not, you know, it also takes a lot of energy and a lot of power. But that's not even the issue. The issue is when you cram a lot of those processors into a room, cooling them is tricky. Just getting air circulation through all of them is tricky. And those of us that are old enough, not you, but me, remember the days when supercomputers, fastest computers around, were liquid cooled. And we may be getting back to that, right? They had liquid nitrogen because you can't put water, right? Because they would short circuit. So liquid nitrogen, which means pressure, and, you know, cool, was circulating through across the boards of computers, literally in order to cool them. And you had a room like this for the computer, for the supercomputer, and then you had another room the size of this room, but on the side that held all the cooling equipment and the liquid nitrogen circulation system. That's obviously very expensive, and we're getting to the point, we try not to go back to that, because that's ridiculously expensive, and on the scale that we're talking about today, it would be even more expensive. But it's not, you know, it's sort of where the things are going if we cannot, you know, if we want to cram a lot of machines in a relatively small space, and then we need to keep them cool, even though they were designed for air cooling. So, and in fact, even now, you have problems such as in a room this size, where you have thousands of boards, blades, right, stacked as closely as possible just to make them fit in the room. you wind up with situations where some of those computers are working more intensely than others. They're computing, right? Whereas some of the others are sitting idle. And so that part of the room is heating a lot more than the rest of it. And getting the air circulation just to that part of the room is impossible. I mean, they're not designed for that. It's very hard to design, right? And this will change over time, depending on the load balance on the programs that those machines run. So people are literally now designing software that tries to take into account, tries to use sensors to sense the power distribution, the heat distribution in the room, and then try to shift the load, to move programs from one machine to another in order to balance the load, not in terms of just getting things computed faster, but simply to equalize the heat distribution in the room. So, and if you don't do that, then you run into problems like malfunctioning. Literally, those things will burn out. Even if they don't burn out today, I mean, in the sense, most of the machines nowadays have sensors for that, for heat. And when they overheat, they will turn off part of the machine or the whole machine. Either it crashes or some of the cores, right? Nowadays, every processing chip has multiple cores. So they will turn off a core. But what that means is the processing power is drastically reduced. So you don't really want to get into those situations. And even if you do that, over time, if this happens a lot to a given chip, just because it got to the temperature where the sensor decided to turn it off, because otherwise it was at risk of burning out, you're shortening the life of those chips. We don't usually see that, and this happens even in laptops, and in desktop machines and what have you. But we don't usually see that simply because we tend to buy new machines every couple of years. And then we junk the old ones, or we don't use them that much. But those chips, so we don't really think about the finite life of the chips inside them. But usually, those machines don't last forever. They last of the order of 5 to 10 years. But if you turn up, if it turns out that the heat is turning up a lot, if they get into situations where they wind up turning off cores, their life is drastically reduced. So you might get, instead of 10 years lasting, or 5 years, you might get 1 or 2 years. Now, this may not seem like a big deal for an individual, but when you have a room full of thousands of those processors, the heat distribution problem is leading to reduced lifespan of those processors. And if you have processors failing all the time, and out of several thousands you will have some that will fail, right? Just because on average it will last 5 years, it means some of them will fail after a few months, some of them will fail after 10 years. If because of heat this is reduced, the whole curve is shifting towards zero, right? And so you'll have some that fail much faster, and then you'll have all of them fail much faster, even though they'll still have some distribution. So this is a very serious problem. It's already impacting us now, and it will get worse in the future for various reasons. Mainly because we continue to make transistors smaller in an effort to get more transistors on the chip, better performance, more cores, better, faster performance. So it's a sort of vicious cycle. One way out of that is, of course, through better technology that's more power efficient, blah, blah, blah. That's already happening, but we're increasing the number of transistors on the chip, and we're increasing the demands for performance faster than where the technology is improving. So that's not enough. Another way to get to the power problem is to try to do that through software, like everything else. Right? So to design software, like I just mentioned, maybe to equalize the load, maybe to move, right, something that's very compute intensive, therefore will lead to the processor heating up, running on one machine, instead of letting it run to completion on one machine, maybe move it from that machine around. Right? simple enough, there's some efficiency in terms of the computation time because it takes time to move it from one machine to another. So, but that's the kind of problems that we're trying to address in the big picture. I mean, this is why it's important. This is why we're looking at power performance trade-offs. Now, of course, so doing it in software is nice. It's in a sense free. It doesn't require new technology other than software technology, right? It requires somebody to program it and come up with various schemes. But it doesn't require new hardware technology, which tends to be more expensive and longer to develop. And plus, this is orthogonal in the sense that you can have faster hardware technology, better, more efficient, more power efficient hardware technology, and the software techniques will apply even to the next generation. Because all we're doing, like in the example of shifting the program around, is completely independent of what, how efficient the hardware is. So whatever advantage we can get from hardware technology, the software can add additional advantage and additional power saving. And power saving, of course, is interesting in its own right because it saves resources, right? So even beyond all those problems with computers failing and stuff, saving power is a good thing in its own right because it saves the environment and all that good stuff, reduces pollution, whatnot. Okay. More down to earth, what is it that we're actually doing as part of this project? We're looking at automatic generation and optimization of performance power trade-offs. So we're trying to make programs, we're trying to optimize the code such that it will not just run fast, but also save power, any program. Now, for some programs, we'll succeed more. For other programs, we'll succeed less. Because certain things make more sense than others. And for some programs, the instruction mix is such that you can naturally make them more power efficient. And for others, it's more difficult. Now, the question is, how are you going to determine that? How are you going to know whether you can help a program become more power efficient or, for that matter, run fast? Oftentimes, paradoxically, the problems are related. That is, surprisingly perhaps, given what I was saying before, you can often improve the performance while also reducing the power consumption. I don't know how many of you are familiar with computers at all, or computer science. How many of you are computer science majors here? Okay, so not that many. So we need to keep this, okay, so I was going to give you an example that probably will not make sense to most of you. So we'll skip that. But very generally, what we're trying to do is we're trying to find, most of you hopefully know that the computer consists of the processing unit, right, the thing that actually does the computation, and it has some memory where it stores data. And then it has some other, some bigger storage device like a disk or what have you. But now, turns out that there's a fair amount of power involved in computing, obviously, and the faster you compute, the more power you consume. But actually, a huge amount of power, probably more than that, is dissipated in loading things, moving things from memory to the processing unit and back. The processing unit has some storage of its own, called registers or caches, but that's fairly small compared to the overall data that the program might manipulate. And so there's a lot of movement between main memory and the processing unit and back. So you load data into the processing unit, you do some processing on it, you store it back into memory. Turns out that consumes this movement of data back and forth, consumes a lot of power. It consumes a lot of power largely because the distances are relatively large between the memory and the processing unit and within the memory, and so there's a lot of power consumption involved in just moving the data around. Now, turns out that there's a lot of optimizations, a lot of transformations that you can do on the code in order to try to keep, instead of bringing data in, working on it for a while, and then moving it back to memory, you can try to bring, and then perhaps later on loading it again from memory, working on it a little bit more, moving it back to memory, and doing this all the time as your program executes. Turns out that you can do transformations on the program so that you sort of concentrate the uses of the one data item in one place in the program. And by doing that, you only bring it once from memory, ideally. You do a lot of processing on it, and then you move it back to memory, and then you're done. So you're minimizing the amount of data motion between memory and processing. And by doing that, you can save substantial amounts of power. Now, it turns out that by doing that, you can also substantially increase the performance of the program, because moving the data back and forth not only takes a lot of power, but takes a lot of time. Memory is intrinsically slower than processing. So by doing, oftentimes, the kind of transformations we're looking at have this dual nature. They will improve performance, and they will improve power performance, power efficiency. It doesn't necessarily mean that they'll improve them to the same degree, by the same percent. So that's where things get a little trickier, because they may be, in some cases, this may be more useful for power than for performance, or vice versa. So what we want to do as a first step, people have talked about transformations for improving power performance while maintaining or also improving execution time for quite some number of years. But what they haven't done is provide tools for people to analyze, or either automatically or by, even for expert users, to analyze the efficiency, to organize these programs so that that you can do this consistently, is what I'm trying to say. So it would be very useful to have a tool that models the program behavior based on some notion of similarity between programs, because it turns out that automatic tools, we want to to ultimately do this automatically, this power performance optimization. But in order to do that consistently over a large variety of programs is very hard, because it turns out that one thing that automatic tools, that this falls roughly under the category of so-called compilers. If you don't know what compilers are, it doesn't matter. But let's just leave it at that. It's a tool, it's a software tool that that takes a high-level language program and compiles it into a low-level language that is understandable to the machine. Now, compilers do a lot of optimizations, largely for performance, but more recently, in the last 10 years or so, there's been more and more attention to doing transformations in order to optimize also power. Now we're trying to do them both at once, because while most of the transformations that improve performance will also somewhat improve power consumption, that's not always the case. And also the amount, there's some trade-offs sometimes. And so it's important to be able to do both, to be aware of both nowadays, but it's extremely hard to make this kind of trade-offs, any kind of trade-offs, to do them in the compiler, in a program that tries to do transformations on other programs. And the reason is that as humans, we are pretty good at dealing with complex trade-offs. An expert that looks at the program for long enough will be able to say, okay, here, power is more important, here, performance is more important, and to make very subtle trade-offs between transformation that would improve one over the other. And that will overall give you both good performance and good power consumption. in a system that is, in an automatic system, it's very hard to make those trade-offs. And it's very hard partly because, first of all, you need a model that sort of includes all the possible ways of trading off one against the other. And also because you need, ultimately a lot of problems in compilers in particular and in computer science in general are so-called NP-hard problems. A lot of the interesting problems, a lot of the hard problems you want to solve are so-called NP-hard problems. What that means is that there are no known solutions that are time efficient. That is, the only known solutions that would perfectly solve that problem, whatever the problem is, require you to try all the possible permutations, which means exponential permutations, which means exponential time, which means very long time for many interesting real-life problems. And so an example from compilers, for those of you that are in computer science, is register allocation. It's just mapping the data that you bring from memory optimally to the small number of registers of fast access data locations in the processing unit is such a problem, is NP-hard. Meaning there is no optimal solution short of trying all the possible permutations for all the data in a program. That's ridiculous. So what people have to do in practice is they devolve to rather simple so-called heuristics, which are just rules of thumb, which you code, and they work well. I mean, they're intuitively appealing. They're things like, well, if I'm not going to need, in the case of register allocation, if I'm not going to need some data item for a while, then I can use that register for something else, is an example of heuristic. And you have a bunch of such rules that you sort of code in your program that does a register allocation, and on average, it will do pretty well. Is it optimal? No. Is it very good? Sometimes. Sometimes it's disastrously bad. Now, a human, in any given situation, if they stare at it long enough, they'll find ways by trading off things, by moving things around in surprising and different ways, will find a way to do better often. Now, the problem is that a lot of the problems we're dealing with in compilers in general and in making these trade-offs between power and performance in particular are of this nature, are NP-hard. And by the way, NP-hard is sort of the holy grail in computer science in that it's a problem that people have noticed that there are some problems for which there is no optimal solution other than trying all the possible permutations. Is something that was noticed maybe 50 years ago. People have intensely worked on this, trying to determine whether there's now a set of problems that is well understood to be in this NP-hard class, but nobody has been able to show either that there can be optimal solutions to some of those problems. And interestingly enough, people have shown that those problems in this set are kind of equivalent in that you can transform from one to the other efficiently. So if you could solve one efficiently, you could solve all of them efficiently. But nobody has been able to, even for one of those problems that have been identified 50 years ago as NP-hard, to show that there is an efficient solution. At the same time, nobody has been able to prove that there can be no efficient solution. So basically, we don't know. There's this whole set of problems that seem to be very hard to solve efficiently, but we don't know that they have to be. Most people believe that they are, that they're intrinsically hard and they cannot be solved efficiently. But the problem is there, and it's been there for 50 years. So if one of you is looking for a research topic, actually this is probably not a good one, because people have tried so hard for so long. And, But the interesting thing is nobody is able to show it one way or another. They cannot show that you can solve them efficiently. They cannot show that you cannot solve them efficiently. Although most people believe that you cannot at this point. Okay, so because of this, it's hard to make those trade-offs. Because of this, it's hard to design a program that will do anything close to optimal, that will look like it's really, really good. So what we're trying to do in this project is we're trying to take a different approach. We're trying to say, suppose you have some problem that you've worked by hand really hard, and you've optimized, and you know that you've done as well as you could possibly do, and you're an expert at this. And suppose you have a set of such programs. Now, it would be a big help, and you know the sequence of steps that you took in order to get to this. It would be a big help if we could say, for a new program that you're examining, rather than have to do everything and analyze it and learn it and optimize it from scratch by hand, it would be a big help if we could say, this program is very similar to this program from the set of programs that we already know how to handle, optimally or close to optimally, by hand. So if I could establish this kind of similarity, then I could try to apply all the transformation that I applied by hand to the original program to the new program. I could do it automatically. I wouldn't have to worry about it. So if we do that, this would be a big step forward. So for that, we need to be able to classify the programs and figure out whether they're similar, and by what metrics are they similar. So we're going to use all sorts of so-called hardware counters. Now, modern machines now have built in all sorts of measurement devices in the hardware. And so we can sample, those are very accurate, but the problem is those will change over the life of a program. So it's not enough to get just a measurement to say, okay, this counter gives me this, this value. This counter has this value at this time in the execution of the program, and over time that will vary greatly, both in terms of power and of performance. And performance itself is divided into a bunch of measurements, right? So there's performance of the memory, there's performance of how many instructions am I issuing at a given time, there's performance of the caches. And I need to somehow aggregate all of those in the meaningful measure of similarity between two programs. Because none of those counters will be exactly the same, and they will all vary all the time in the programs. So how do I determine similarity? Well, I have to apply some statistical techniques. And for the purpose of this discussion, I think, and given the time, I think that's where we'll stop, except to say that what makes this research is that nobody has come up with such tools that can do this very well, and certainly not in the context of power-performance trade-offs. So this is why it's important, this is why it's interesting, and this is the project that Andrew is working on. Now, what other things am I doing in terms of research? Various other things that are very different from this. I mean, there's some things that are related to this. We're looking, for example, at Java interpreters. Java, as you know, probably even if you're not a computer science major, you've probably heard about Java being a relatively hot, relatively new, let's say 15 years, programming language that has been touted by many as a panacea for various things. It's not, but it's a good language. It's probably as good as any. It has some advantages. It has some disadvantages, but it's hot. I mean, people use it primarily because of portability issues. Theoretically, Java programs are very portable, and they don't have time. And for those of you who are not computer science majors, it's not that interesting why that is, but it's a reasonably interesting, reasonably good programming language that is used a lot. And therefore, it's hot in that sense. Now, the problem with Java, the portability in Java comes at the expense of execution time. It's relatively slow because it's interpreted, and again, I don't have time to go into why portability implies interpretation, and even what interpretation is. But it's not as efficient as code that is executing on the bare bone machine. This is executing on a virtual machine and so on. So the virtual machine has implications for power, has implications for performance. There's ways to optimize that performance. And we've been working on techniques to do that, various ways. Another thing that's totally unrelated to either of those things is, except for performance, which is sort of a running theme, but then that's a running theme in most of systems related research in computer science, meaning hardware, software, is matrix multiplication. Surprisingly enough, right, matrix multiplication is a seemingly utterly trivial operation, right? For those of you that have taken any math course, any algebra course, you know what matrix multiplication is. Turns out that matrix multiplication is a very important problem because it's at the core of virtually every scientific computation. Not all, but many, many, many scientific computations are at heart involving big matrix multiplication. Now, matrix multiplication is fairly trivial to write. It's a 10-line program, maybe less, 3 nested loops, and the line in the middle. Right, so 4 lines, plus some declarations. So it seems like a weird thing to do research. Now, furthermore, people have come up with an algorithm, which is the 3 nested loop, as soon as they had computers, because some of the earliest uses of computers were for doing scientific computation. Right? And scientific computations are, of course, important for everything from doing Wall Street, stock market predictions to simulations, to designing planes, right? Doing simulations of airflow around the plane, the wings, what have you, to weather prediction, to drug design, to new material science, whatever. So all of those things are very important. To cell phone, signal encoding, decoding, you name it. So all of those things are clearly important applications. Therefore, matrix multiplication is very important. Therefore, it's something that people have worked on, very smart people, for 60 years or more, and making it efficient. So you'd think that by now, there wouldn't be anything left to say on such a trivial, simple, well-understood, old algorithm as matrix multiplication. Well, surprisingly, perhaps, it turns out that there's a lot left to say. First of all, it turns out that the 3 nested loop implementation of matrix multiplication is a horrible way to execute matrix multiplication on virtually any modern processor. Leave alone the fact that you have multiple cores, which is a separate, parallelism is a separate complication on its own. But matrix multiplication, first of all, there are different algorithms for doing matrix multiplication that are asymptotically better. That is, for big enough matrices, they're definitely superior by a lot. Faster. Turns out that because of the nature of modern processors, mainly because modern processors tend to have a main memory that is big, then they have a cache, and perhaps another cache, and perhaps another cache. Most processors nowadays have 3 levels of cache, plus registers. Turns out that executing the 3 nested loops is an absolutely terrible idea, unless, in terms of performance, unless you do something called blocking, which is you break the matrix into smaller chunks that will fit in the various levels of cache recursively, right? So because each level is smaller than the previous one. So that's one thing that people have done. And so, but if you do that really well, there is a crazy guy who used to be at University of Texas, Austin, who has done that for like the last 15 years. And he had given up for a while and moved to Microsoft to do something else, and now I just heard he was hired from Microsoft just in the last year. He moved to Microsoft, and now he was hired by Intel to work on matrix multiplication again. They have a group of like 50 people at Intel that is working on matrix multiplication. And so this guy for 15 years has been tweaking by hand. Not entirely by hand, he has partly automated it with some macros and stuff. But all he's been doing is tweaking the 3 nested loops into blocking, but doing it really, really well from the register level down to memory. And the code from the 10 lines or 4 lines, depending on how you count, is mushroomed to 3,000 lines. That not many people can understand. I mean, the code is available. It's publicly available. There's not many people who understand it because it's just complex. And the mathematics involved are complex. And the computer science involved is complex. And it depends on little hardware details. And so there's not a whole, and all he was doing with this, and probably what he'll do for Intel now, is every time there was a new machine, he would take his 3,000 lines of code, most of which are general, are written in a high-level language. About 400 lines are written in assembly for every new machine that comes out. And he has macros to generate it because it's very regular. It's trivial code in some sense, matrix multiply. But so he tweaks it and tweaks it and tweaks it, and nobody has a matrix multiply that runs faster than this guy, except us. So, and the way we do it is by cheating, by switching to another algorithm that is asymptotically faster, that is better for that than what this guy was doing. Now, this asymptotically faster algorithm has been known also since the mid-60s, late 60s, right, 1960s. So it's not exactly news. Why did nobody else use it? Well, people tried. But the common wisdom was that the algorithm is in principle asymptotically faster, but the constants involved, right, the overhead, so to speak, is much bigger. And it's much bigger precisely in the memory hierarchy, in dealing with the memory hierarchy. As a result, people believed that for any size matrix that you can fit on a machine, those algorithms are impractical. Right? So even though in principle on an ideal machine that doesn't have a memory hierarchy, this will run well, in practice, on any given machine, this would not run well. So it was considered sort of worthless. Now, all we've done is realize that for large enough matrices, doing a little bit of this asymptotically faster algorithm will give us just the right boost in performance and just the right trade-off between minimizing, because what this algorithm, what asymptotically faster means, is it does intrinsically fewer operations, intrinsically fewer multiplies than the other algorithm. But it requires more storage, and therefore it's more inefficient in the memory use. By just doing a hybrid, by doing a little bit of this asymptotically faster algorithm, and then invoking this guy's Goto, by the way, is his name, Japanese, algorithm, after that, we managed to get the best of both worlds, and by doing it just right, we managed to overall increase performance for large enough matrices that do fit in memory. So that's sort of an interesting result. Then the problem is, research is never straightforward. It's never simple. So we can get better performance. Now, the problem is that the way we're computing the matrix now with this other algorithm, and I don't want to go into the details of that, but we're changing a little bit the order of the operations. In so doing, we're actually losing a little bit of precision, because machines having finite precisions, computers having finite precisions, doing operations in one order and doing them in a different order may affect the precision. And it so happens that the way we affect it is we don't increase it, we actually decrease the precision, for reasons that weren't entirely obvious for a while. We now manage, by adding another layer, a third algorithm to this matrix multiplication. So now we have 3 levels of matrix multiplication. So we have the 3,000 lines of code that Gottes comes up with. We have another layer that doesn't improve performance, but actually improves precision. And then having this other asymptotically faster algorithm that improves performance, we can manage for a certain size, for large enough matrices, we can improve both precision and performance. So, but this is the result of 3 years of work. Graduate student with a couple of professors. So this is research. Right? So, you may think, it's not everybody's cup of tea research, but this is some of the stuff we're doing. Very briefly, because I guess I ran out of time. Well, how did I get here? Well, I went to Brandeis on the East Coast and got a BA in computer science and physics, partly because at that time, which was 77 to 80, computer science at Brandeis was part of the physics department. Physicists think they know it all, and so, Brandeis wanted to introduce a program in computer science. They didn't know where to put it. The physicists said, we can do that. We can teach that. As a result, I had an absolutely horrible computer architecture class taught by a physicist. And I was in a total fog throughout the course. And luckily, there was a friend who took it before and gave me his project. And then I could, just by looking at his project, I could understand what the guy was trying to say in class about computer organization and whatnot. Anyway. So I got a double major in physics and computer science as a result, with very little physics and a lot of computer science, some of it taught by physicists. Then I went to Yale, and I went to Yale because I wanted to do artificial intelligence, and in particular natural language understanding. And at the time, there was a guy at Yale named Roger Schank, who was one of the founders of the field of natural language understanding and then cognitive science. And he's the first editor of this journal that he introduced, that he created, called Cognitive Science. And he was a really big shot in the field, still is to some extent. He's moved on to other places. And he's getting old. But, after going, so I went to Yale to do that, but after taking an AI course and as a graduate student, right? That was a PhD. Now, after taking a course with one of his disciples and having a talk with Roger Schank, I decided that AI was not really a good idea, partly because of the guy's personality more than anything else. And so I winded up essentially somewhat randomly picking this field of optimizing compilers, which partly because there was a relatively young guy there, assistant professor, who just got a grant and had some money to support me, and he was looking for students, so it was a match made in heaven. And initially I wasn't very crazy about working with a guy, and he wasn't particularly crazy about working with me, but there we were. So in the end, it all worked out, and I got the PhD relatively fast, in 4 years, which by today's standards is a record, but back then it wasn't that. The older a field becomes, the harder, right? I mean, all the easy research has been done, and it becomes harder and harder, and it takes longer and longer to do a PhD. So nowadays, the average is more like 5.5 years. And in more established fields like physics and maths, it's even longer. There are exceptions, and right, there are geniuses, and oftentimes people manage to do, right? I mean, you just luck out. In fact, I largely lucked out in the sense that everything I've done from when I started doing research to my thesis sort of fell into, were pieces of a puzzle that fell into place, and the whole thing was my thesis. Sometimes people are not as lucky, and you do something and it doesn't pan out, and then you have to do something else and it doesn't pan out, or you pick something that just takes a lot of development. I had a student here who, that was sort of a sad case, but she worked on for 8 years and then eventually quit without a PhD thesis. And it's not, she was a good student, she was doing good work, she had publications, but they didn't really fit into a coherent thing. And the one thing that she really wanted to do, and I tried to discourage her because I thought it was too ambitious and too big a project, but she insisted on wanting to do that, was just too big for one person to do. And she was making steady progress. It just was very slow. And then eventually, they moved the two-body problem. Her husband got a job on the East Coast. They were both from the East Coast. They decided to move back, and she never finished the PhD. That's usually, for most people, don't let that discourage you, however, because for most people, if they work hard, they get a PhD. Even though a PhD, unlike a BA or a master's even, is a totally different beast, right? You need to do something to substantially advance the state of the art, whatever that means. And it's usually something that you and a committee and your advisor eventually agree on with some negotiation in the process. So anyway, let me stop blabbering now. And if there's any questions, I'll take them. If not, we'll quit. And then Andrew will tell you something actually interesting at the end of the summer.